3, 2, 1. Hi everyone, my name is Siamak and welcome to ACigs webinar series, Australian chapter of the International Geosynthetic Society. This is webinar 17, 10th of March 2021. So welcome again everyone. ACigs is the Australasian chapter, and as you can see in the map, we are part of the Global Society of IGS. You can become a member of IGS through the chapter. So we encourage people to become chapter members through your regional chapter. So in Australasia, we encourage people to become a member of ACigs, and then you will automatically become a member of the Global IGS. And as you can see, the little red circle on the IGS website shows you the technical resources. So there are many resources available to the members of the International Geosynthetic Society that you can benefit from that as a member. And this one here is the ACIGS website. So the address is up there, www.acigs.org. As we announced in one of the recent bulletins, we are upgrading the website. So there will be a new look and a lot more user-friendly and more resources available to our members. So we are all looking forward to the new upgraded website very soon. One of the main or important content of our website is actually the recording of the webinars. So we started these webinars in 2019, and as I said, we have had 16 webinars so far, and today is webinar number 17. So all the recordings are available to our members through the website. You can also request a certificate of attendance for this webinar at the end. So you just need to email info@acigs.org and we can make that provided to you. And today's webinar, so we have Geofabrics as our sponsor, and Corey Housing is representing Geofabrics today on our panel, and Corey will present a case study at the end of Erol's presentation. So thank you to Geofabrics for their support of this event. And the title for today's webinar is Ballast Stabilization and Mitigation of Ballast Degradation using Geogrids. This will be presented by Dr. Erol Tutumluer, professor at University of Illinois. Just a very brief introduction of Erol. So Dr. Erol Tutumluer holds a bachelor from Boğaziçi University 1989, 2 master's degree from Duke University 1991 and Georgia Tech 1993, and a PhD from Georgia Tech 1995, all in civil engineering. He has been on the faculty of the Department of Civil and Environmental Engineering at the University of Illinois since 1996. So Erol specializes in transportation geotechnics with research interests and expertise in characterization of pavements and railroad track geomaterials, subgrade soils and base, ballast, unbound aggregate, soil aggregate stabilization, geosynthetics, modeling granular foundation systems using innovative techniques, sustainable use of foundation geomaterials, and construction practices for transportation infrastructure, discrete element analysis of ballast, dynamic response measurements, and analysis of track systems and mechanistics analysis and design. So with just a little sustainability quote, because as you know, sustainability is the theme this year, 2021, for our chapter. The quote is, "Sustainability is no longer about less harm. It's about doing more good." So hopefully we all do more good for our environment. I stop sharing from my end and floor is yours, Erol.
Sure, let me put mine on and hopefully you can all see my presentation now. The first slide, title slide.
Yes.
All right, thank you very much for the great introduction, Siamak, and I would like to thank the Australian chapter, IGS, for inviting me for this webinar. And it's actually a pleasure to see so many attendees for this webinar today, coming from different parts of the world, in addition to Australia. I would like to talk to you about today the ballast stabilization and mitigation topic, especially using geogrids and how actually geogrids are useful in not only stabilization, but also extending life, the sustainable application very much of using geogrids and stabilizing these ballast layers. I come from University of Illinois, where I do research associated with the Illinois Center for Transportation and Rail Tech, our railway engineering center. So with that, actually, I'm really lucky from the perspective that two transportation centers that I've been affiliated with and doing research on these topics that you heard from already, CIMAC. So with that, let me start by quickly introducing you to the railroad area, especially from the perspective of US and the United States and comparisons to Australia as well. But railroads is a single one entity here, is the principal mode by means of economically moving large and heavy freight long distances over land. You see a typical unit train carrying coal from the west to the east in this case in the US. And with that function, actually, rail has the speed and energy efficiency for carrying large and heavy loads. In addition to unit trains, we have oil trains these days, as well as intermodal cars that you see carried. And with that, what I'd like to mention is that with Australia, probably United States is coming as the second in terms of the density of the freight trains, and from the perspective of actually carrying a lot of freight on trains. And the heavy axle loads, heavy haul designation that's actually been very much related to all the freight rail network that you see in the United States, with many roads actually going over 50 million gross tons of freight traffic per year, and quite heavy axle loads, only again second to Australia in that. And sorry about that, little bit of problem here. Let me go back to my sharing. I think I jumped out of sync here. All right, wrong button to push. I should not be doing that. Perfect. What I'd like to do here is a quick comparison between United States and Australia. In terms of the land, they're not that different, the two countries, but of course, population-wise, Australia is much less populated. And the dense network of the rail you see here in this picture, especially freight rail, the only thing that matches is the east-west lines. That is primarily actually in Australia carrying a lot of load, a lot of freight on 36,000 kilometers of track compared to about 6 to 7 times larger network in the US, almost 220,000 kilometers. But if you look at the million or billion metric tons of freight carried per year, US and Australia is very comparable. Again, the idea of the freight rail taking the heavy loads and the heavy loads going down in the track substructure, and how we can use geosynthetics in that remediation, in that actually a ballast stabilization topic that we're talking about. Another slide here that shows you almost 95 to 96% of the all rail network that you will find in the US owned by the freight railroad companies. And as such, therefore, a lot of the cases, passenger rail, passenger trains have to share the trackage, the right-of-way, and almost all the time, because these are originally freight lines, these are ballasted tracks, not dedicated high-speed passenger lines. So we are really limited to upgrading or increasing the speeds and upgrading the track classes on some ballasted tracks. When we talk about, therefore, ballasted tracks and the track substructure, these are the multi-layers that actually carry all the load, especially ballast and sub-ballast are granular materials that are supposed to be distributing the load that's coming from the wheels, from the train rail, and directly into the track substructure. So upper ballast layer serves the drainage purpose and also lateral stability, holding the sleepers and the rail in place. But at the same time, subballast often is a separation layer that actually provides that intermediate layer of separation, that intermediate layer of drainage in a way, not to allow fines coming into the ballast layer, right? When you think about, therefore, the basic principle of ballast and subballast granular layers, like in most of our road structures, carrying the load and distributing the load, typically in the US, ballast thicknesses go from 23 to about 38 centimeters or so, and subballast in the order of 8 to 15 centimeters, and they're supposed to protect, basically bridge over and protect the subgrade, which is usually the weakest layer. Especially two forms of failures related to subgrade going into some kind of a high excessive deformation. These are either progressive shear failure or excessive plastic deformation type failure. So in the case of progressive shear failure, always the load coming directly from the rail and causing that clay subgrade, that cohesive subgrade, basically going into in a progressive bearing capacity type failure that you're seeing in this slide. Or if you have, again, somewhat excessive loads coming, not necessarily, stresses that are distributed well and limited in capacity that are going on subgrade, and then those excessive stresses, these are typically over about 20 psi according to ARIMA in the US, can create easily some of those excessive deformations right on top of the subgrade. And with actually the deformations causing, deformations happening in the exact rail locations, this is the position for trapping the water and creating water pockets. With water accumulating in those locations, then you're further softening and weakening the subgrade to cause excessive deformation. These two types of failures are very common in subgrade conditions, and that's where actually for subgrade stabilization, geosynthetics will do a great job for us, especially again stiff geotextiles, or my topic here is really on geogrids from the reinforcement from the stabilization perspective. So in that application of soft subgrade stabilization, where we put geosynthetic is typically the bottom of the subballast layer, and improving therefore the bearing capacity of the soft subgrade and bearing capacity of the system. Right. However, I'm not going to talk about subgrade stabilization in this presentation. I will more focus and concentrate on ballast stabilization, and the reason of that why is basically very nicely shown in this slide. This is from 2016, Association of American Railroads, basically in the umbrella organization of Class 1 or all freight railroads in the US. This is a research review that took place where actually all the different research efforts were showcased in a way. And at that time, from Transportation Technology Center, the subsidiary of AAR, Colin Basie presented this just to show the percent cost distribution that is dedicated to track substructure expenses, altogether over 2.4 billion per year. And if you look at typically where actually that money is spent, about 40% of that goes into ballast renewal, ballast maintenance, maybe 15% to other substructure maintenance could be related to subgrade, and the rest goes up to rail and the ties or sleepers, right? But 40% is a big number, and this is where actually ballast is a major cost item overall in building track substructure. And the other thing, fascinating thing about ballast is that ballast is typically uniform sized, as we all know, and this uniform side with large void structure taking the load gets the heavy pounding, actually channelized load under the rails. And with that, typically the aggregate materials starts to break down, starts to abrade and break down. And that's how the fine materials are created. And fine materials slowly actually cause the consolidation of the ballast to densify, but at the same time with fines increasing in content like this, what we call as fouling. Fouling of ballast takes place. What then practitioners refer to this as fouling is that basically, depending on the definitions, practical indices that were developed related to the percentage or amount of fouling, right? How bad ballast particles become in terms of fines now start to separate those larger particles apart, which is the main mechanism that's supposed to carry the load, right? Professor Ernie Selig's two indices, fouling index and percentage of fouling, you can clearly see here, very common, and a similar index was developed in Australia as VCI. All these indices help us to regulate and understand the maintenance times of ballast material as ballast degrades. Because if we don't maintain and properly take precaution, there are some conditions that take the railroad track to failure, and we never want that to happen. Poorly draining or non-draining ballast will cause these water pockets ponding basically right on the surface of the track, or pumping associated with a lot of the dynamic loading coming from trains, and now I guess you don't have a proper geosynthetic separator, right? Subgrade can pump, or sometimes, most of the cases, 76% of the cases, what you see as fine material pumping here on the surface is typically degradation of the rock itself, powders. It turns into powder, and it becomes a very challenging topic and challenging task for us, because failures come in fouled ballast just like that. Can geosynthetics improve the load bearing and stability, and especially those fouled conditions with a lot of moisture? Yes, geosynthetics can do that. Geosynthetics can actually further help us in other maintenance solutions, such as typically shoulder cleaning and undercutting. Shoulder cleaning is a preventive maintenance in a way. Basically, the drainage takes place from both shoulders, and if you end up cleaning and renewing the ballast on the shoulders, you're actually helping the drainage paths to open up again. That way, the pumping and associated ponding issues will not happen, right? But if the ballast is completely fouled with a lot of fine particles, in that case, undercutting, basically renewing all of the ballast with new ballast and maybe some recycled ballast in this case, is a typical scenario in maintenance application that's applied. Undercutting is a major cost, some 6, 7, 8 times higher cost sometimes compared to shoulder cleaning. And when this is the case, we want to actually delay the undercutting need. And that's where geosynthetics come to mitigate the ballast degradation, and therefore much, much less frequent maintenance cycles we need and longer life with ballast. So what is more sustainable than this is hard to find. It is indeed a maintenance extension application than what we use geosynthetics for in railroads as ballast stabilization application you see. So in that case, we just move the geosynthetic up to towards the bottom of the ballast, right? That's exactly where it's contributing to improve basically the life and the life cycle of ballast. Why? Because ballast particles, individual particles, aren't supposed to be moving, and the geosynthetic, and probably best done with geogrids, are supposed to hold them in place to keep the ballast particles through attrition and through movement not degrade, and actually keep in good condition. So there have been numerous applications of this. A lot of these that you see in these photos, for example, go back to some European applications, and you can clearly see how under the ballast they're laying down a geogrid, either here a rectangular grid, rectangular aperture, or a triangular aperture grid. And this is a typical ballast stabilization application. Again, when we do this, the identified mechanism we need to understand very well. Basically, out of the 3 established mechanisms associated with granular materials and geogrids or geosynthetics in general for reinforcement and stabilization, the most relevant one is, as we know, is called lateral restraint. That is, you're basically minimizing the tendency of those unbound aggregate particles to move and displace laterally. And by doing that, you're minimizing their movement under the applied dynamic loading, and as such, they break down much less, right? So it's a win-win scenario for extending the life of your ballast. Now, a direct function of the ballast stabilization is increasing stiffness in the zone where actually you're arresting the movement of individual particles and you're not allowing, again, basically to the sides, the movement of the ballast under the applied loading, wheel loading. As that's the case, even in the initial construction and compaction conditions, as well as throughout the life of the ballast, there's a stiffening that's achieved right here towards the bottom of the ballast. Why I keep showing the bottom of the ballast is where you put the geogrid in this example. Well, because especially ballasted track gets a lot of maintenance with temping tines, right? The geometry corrections and railroaders want to do that often. So you want to extend, you want to basically put the geogrid, in this case, far away from the reach of those temping tines. And that's typically for our concrete sleepers or ties, in our case, about at least 8 inches or 20 centimeters below the bottom of the tie is where you should place, your geosynthetic or geogrid material. But typically towards the bottom also works. Now, why does that work, and why does it really create a stiffening effect? Increasing the modulus, right? Stiffening. Very interesting work done over in Europe. And I was part of actually this European Geogrid experts panel meeting back in 2013. Researchers, Professor Horváth, actually in Hungary, they built this multi-level shear box, which is a very interesting concept. Basically, you could just adjust any location in this multi-level shear box to go through and do the shear testing, like a similar, simple shear box concept. But now you can change the horizontal axis, horizontal line of the shear. So by actually shearing the material at different heights above a geosynthetic place, right, you can actually understand how at different elevations above the geogrid place, maybe the stiffening is taking place. This was really a very clever idea. And according to what they found, very interesting. This clearly is a lab validation of geogrid stiffening above, for example, here is the shearing plate where the geogrid is placed, about how much force that you can clearly see in this picture is generated. In an uncompacted aggregate ballast layer, you see with geogrid, without geogrid, with geogrid cases are red color in this case. You always have higher shear resistances and pushing force. But in the case of a well-compacted one, there is a certain almost 10 centimeter zone above here that is extensively increased in stiffened in modulus or increased forces that will eventually cause a stiffening effect right here in that zone. And that stiffened zone is something we like to understand because that's where everything is stationary, particles aren't moving, and you have enhanced the modulus and stiffened. Therefore, that zone due to installing the geogrid. And that goes back to the concept of then mechanically stabilized unbound aggregate layers. And here, the mechanically stabilized ballast concept. By putting a geogrid, for example, towards the bottom of that layer, of that ballast layer, you're creating a mechanically stabilized layer of increased stiffness just directly above, and then gradually that stiffness decreasing to actually typical aggregate stiffness or modulus values, right? By doing that, by actually increasing the confinement now directly under where the wheel load is applied on that rail, you're typically increasing the load taking ability, you're increasing the stiff, you're decreasing the long-term permanent deformation accumulation within the ballast. That's through the degradation and settlement aspects. And all of that is happening with grid beautifully preventing, again, aggregates moving around, the lateral restraint mechanism. As I said, this is a very sustainable application as we list the benefits of ballast stabilization and performance, right? Decreasing the time-dependent settlement by first at the time of construction by increasing the modulus of that ballast layer, and probably more importantly, throughout the life of that pavement and now for an extended life, you're minimizing the degradation of the modulus of ballast over time. And exactly that's what actually, if you're not decreasing the thickness here, that's exactly what increases the life expectation of that ballast with the ballast stabilization application, which is in green color, 100% sustainable in my opinion, because you're getting so much more life out of that ballast layer constructed. Excellent. Some typical applications of ballast stabilization efforts around the world. When you look at the beginning of this millennium, there's been a major study done at Nottingham University in UK, and actually a study that went back to even generating different geogrids, having different aperture sizes, and seeing what works the best in actual lab environment where different types of, you see concrete sleepers or ties with actuators loaded, and with the typical geogrid placed under the ballast, how settlement is actually minimized, right? And here's an example of what they found after so many hundreds of thousands of cycles in that setup in the lab. In the case of a control, you have much higher settlement, and much less settlement is generated in general with the geogrid stabilization of that ballast layer. So this is a typical advantage right here. At any point, you can clearly see the number of thousands of cycles going from maybe 300,000 to, in this case, 700. This is a major life extension that we are talking about, right? For the same amount of deformation expected. A follow-up study, actually by Steve Brown, Professor Brown, who took the lead in this study at Nottingham at that time, he was able to also look at the condition of an actuator setup like that with actually a kind of a tie here you would consider, but this is more like a steel beam, right, loaded under an actuator. Here is a ballast and there is a load cell. By placing a geogrid in this ballast, right, in this ballast layer that's created here, just like that shape, with the typical ballast used, in this case, they had about D90 of about 50 millimeter typical size of ballast, right, with those gradation properties. The idea was how to go about having different aperture square grids in this case, but different size square grids to see which one will actually decrease the deformation the most and would probably work the best in terms of matching with the gradation and size of those particles of that ballast. So basically what you see in the second case is the aperture opening of the square geogrids, 32 millimeter, 38 millimeter, 50 millimeter, 90 millimeter, 100 millimeter. What they found was that at about 30,000 cycles of loading, really the lowest that they obtained happened to be actually with a 65 millimeter aperture corresponding to D90 of a 50 millimeter typical ballast used in UK. Based on that, Professor Brown came up with a size of geogrid aperture, therefore should be 1.2 to 1.6 times D90 for the best performance. See, some kind of an optimization of the aperture and the ballast particle size, and probably shapes need to be involved here. So right about that time, with the same, these are called kind of SS grid, square grids, more field studies were taking place in UK, and another study that took place in actually western coastline in UK. They were putting down geogrid at the bottom of a new ballast layer and looking at typical maintenance cycles, basically the rate of settlement data. And quite interestingly, what they reported was that compared to that problematic line, always giving in many years, one after another, 1.4, 1.5 millimeter per year type of deformation rates, right after installing the geogrid, that was dropped down to 0.4 millimeter per year. So this is an amazing, again, life extension and sustainable application, in my opinion. Now, The same person, Phil Sharp, actually in UK, he was also instrumental in getting multiple layers of geogrid used in a bridge approach application. And this was a tapered concrete slab, further strengthened with multiple layers of geogrid that actually killed a lot of that bump at the end of the bridge, the differential settlement problem. This was a very well studied and actually instrumented section here that showed a good performance, a typical case history that we always use. Going over to Australia now, and I highlighted the title in green because Professor Indiradna has been doing a lot of work on ballast, as you all know him well in Australia. One of his applications that I'd like to highlight here is that both fresh as well as recycled ballast used in this field instrumentation site, the track, the town of Bully. This is where he was able to see side by side the effect of a geogrid and geocomposite, basically with the geotextile geocomposite reinforcement or stabilization of recycled and fresh ballast. And interestingly, Professor Indiradna actually in 2010 study here concluded that recycled ballast, because it's broadly graded compared to the uniform fresh gradation of new ballast, performed even better. That was very encouraging. And he also found that optimum aperture size of geogrids is about 1.2 times D50 now, not D90, D50 of ballast. Interesting, right? How about in the US? In the US, the approach that we have in our American Railway Engineering and Maintenance of Way Association, ARIMA manual, basically is governed by this equation, which is the thickness of the layer below the bottom face of the sleeper or tie, according to the pressures, that how thick of ballast and sub-ballast layers you have to construct. That goes back to another UIUC professor, just like me, Professor Arthur Talbot from 1920s. Very, very well-known figure again in railroad engineering. So in that ARIMA manual, as of 2008, there was a new section added on geogrid stabilization of ballast and sub-ballast. So we have that option in there. And with that option in the US, we have had several projects constructed. Then, for example, this one is the Utah Light Rail project that with the addition of geogrids and the sub-ballast decreased the thickness from about 30 centimeters down to about 20 centimeter thick. So this is one advantage, if not associated with life extension, right? Decreasing or reducing the thickness of the granular layers. Another application here in a typical staging track yard that you're seeing here, 10 inches of ballast, 8 inches of sub-ballast, again, typically 25 centimeter versus 20 centimeter, right? I forgot to change those into centimeters, all right? Triangular and rectangular geogrids used in this case, and they were installed in this track where actually the study had to do with how much deformation settlement would take place, right? You can clearly see those marks that are surveyed here as for the typical tie settlement or sleeper settlement. But more importantly, there was a pressure cell installation site, and the pressure cells, these are subgrade pressure cells, were typically showing under two different types of biaxial, triaxial, or rectangular aperture versus triangular aperture, how actually there was differences in bridging of stresses over the subgrade when these geogrids were used in ballast stabilization. Very interesting. More importantly, I guess more recently, I should say rather, but this has been a long study that was taken by Association of American Railroads, a site called Captina site over in Ohio. And this was actually an embankment that had some moisture issues, but very frequent maintenance cycles for ballast. Ballast pockets and some weak subgrade with moisture issues, right? This was a site that was highlighted back in 2012 to 2016 with maintenance requirements, very frequent. So by installing a geogrid in this site, actually, that's typically slow down the maintenance cycles, and there was much better cost benefit and extending life of that ballast. Later on, though, they found that there was some movement of the lower embankment as well. But cost-benefit analysis concluded in 2018 still shows a lot of the benefit of the geogrid placed in the ballast layer. So in some of my work at University of Illinois, just to focus on those quickly, I have been studying in the lab a lot of these aspects that were put forward for us back in 2009 when the Jubilee Symposium, the 25th anniversary of Geogrids, were discussed in a symposium over in London. And at that time, Dr. Giroux came up with the concept that it is not just the geogrid types, the aperture and the shape and the properties, but we need to match the aggregate size, gradation, and shape properties, as well as compaction efforts and loading conditions. So that's been really the challenge with me because, well, what kind of challenge you will say? Throughout my career, I've worked on aggregate characterization a lot, and we have developed this aggregate shape property characterization tool as an image analyzer for aggregates. With 3 cameras, we're able to capture actually the views of aggregate particles and come up with quantifiable indices. But most importantly here is that with 3 orthogonal cameras, we were able to build some 3-dimensional polyhedrons in this case that we could nicely incorporate into our discrete element models, right? One element becomes one particle, and you can exactly capture the typical ballast properties to put into your model. And that's how we studied the settlement or other lateral stability or temping issues, all kinds of issues we've been studying, including recently some of the triaxial testing work as well. One of my students recently graduated, actually way back, looked at the study by Professor Brown, and we were able to come up with a discrete element model of his setup of the ballast materials. And we were able to replicate even up to 40 cycles in this. At the time of the 40 cycles, what actually Professor Brown found the 65 millimeter aperture size really decreased and gave the minimum least settlement. We were able to simulate that with that kind of model. Of course, more of this was directed towards, in the past 10 years, we developed a triaxial device, and triaxial device used for testing ballast in shear strength as well as permanent deformation, right? This is a typical 30 centimeter diameter by 60 centimeter high cylindrical specimen, actually with 3 different LVDTs around, capturing basically the vertical displacements as well as a circular circumferential LVDT just to catch the bulging in typical permanent deformation tests. So we have been running a lot of tests on different ballast particles, and especially with geogrid reinforcement or stabilization, typically in the middle where the bulging is, right? But we tried different locations as well. And interestingly, we studied quite a bit actually using this setup, such strength and permanent deformation properties of ballast. In this quick video, you see our rapid shear strength test, which is quite rapid, 5% deformation per second. And you can clearly see actually how you fail the specimen. And by putting in different locations, different types of geogrids, we were studying the stress strain and basically strength information. Of course, as you can imagine, when you place geogrids directly in the middle where the bulging is, you get the highest strength improvement. And especially with 2 geogrids close to the middle, that's when we got the highest, or the highest strength, I should say, or the best performance, right? Same thing with rectangular grids as well as triangular grids. And eventually we put them into this very nice discrete element model simulations, where actually the sample is created exactly the same way as we create the sample, make the sample in the lab. And what you see around here are those membrane elements that are frictionless and that can allow the bulging. They're just sitting on top of each other. They're large because they can be pushed out, but they're not supposed to fall out. So that's how, by putting them in the middle here, you see a triangular grid or a rectangular grid. We're able to see and simulate the effect of a geogrid stabilized ballast specimen testing effort. And if you can see here, you can clearly see how that testing will simulate the bulging effect of those membrane elements and how those actually look very much similar to what we found in testing, right? Of course, you need to mesh the strength values, and we were able to do that very well too. And one thing that we published back in 2014 here in a paper where we analyzed, if you look at those different membrane elements and how they're moving around, basically that told us where the bulging is as expected in the middle, right? And that's really where you need to be putting the most geogrid, or where the geogrid needs to go. Again, one in the middle is quite good. One on top, one at the bottom, but far away from the middle section of bulging, that's probably not that great. Of course, this is unreinforced. It's even worse than unreinforced, right? But here you see with two geogrids going in the middle, you get the highest strength achieved from both the tests as well as the DEM simulations, which are actually the typical data points you see in these plots. Another example of that with two different geogrids, how we did the permanent deformation simulation of a triaxial test. You can clearly see no geogrid, and in the geogrid cases, we see much lower permanent deformation accumulation under such repeated loading cycle, right? So these are the effects, or these are the efforts really that helped us to pinpoint some of the factors affecting the interlocking, understanding therefore aggregate shape and size and how they contribute to the stiffened zone, and by actually properly simulating the size and shape of the aggregates and that of the geogrid, right? We can play a lot of games, and we can do a lot of what if scenarios with this kind of a discrete element too, which indeed we have been actually coming up with a lot of conclusions from that. Nevertheless, one point I like to highlight towards the end of my presentation here, which is when you think about geogrid stiffening, and the question still comes up as when is that best achieved? If you look at different researchers, okay, they all come up with different type of recommendation for you. And sometimes the size to aperture size to aggregate size correlation does not come together very well, and they don't agree with each other. There is still a lot more to understand on this. And my last topic here, just to mention to you, is that with that in mind over the years, I put all my efforts in a goal that how can we measure that stiffened zone, which is we know what's happening, the stiffening effect. And we went to seismic techniques. A bender element shear wave transducer is something we developed for actually measuring small strain modulus or local stiffness of that geogrid stabilized zone. For that, we use the very well-known bender element technology, which is consisting of a piezoelectric sheet. When given the voltage, basically the piezoelectric sheet vibrates. It's almost like the fishtail, right? That's how it's creating in the medium it is buried in. A shear wave, the shear wave travels and picked up by the receiver set or receiver on the other end. So therefore the two as a set will work as generating the source of the wave and receiver of the wave. So actually piezoelectric sheet is right here in this mounting base. That's a typical instrumentation we came up for instrumenting a triaxial cell. Right here we have three levels of three pairs shown above the midsection of a typical specimen. And the midsection, if you place a geogrid in the middle, let's say, you can actually send those waves through wave generator, signal generator, and pre-post amplifier and an oscilloscope and detect during, for example, a modulus test. After finishing some of the modulus cycles, now we're doing a shear modulus measurement. Very interestingly, those three levels above the geogrid could show us the shear wave velocity measurements turned into, converted to shear modulus, can show us here a much higher stiffness directly above the grid and decreasing amount of shear modulus values as you go away from the geogrid, right? And if you look at with no geogrid case, from all three pairs, we're getting exact same shear modulus. So that means there's nothing changing. But with geogrid, there's everything changing. And that local stiffness measurement, we were able to basically measure in this setup, and we were able to come up with about that grid. You can see the mechanically stabilized there. You can actually generate like that. And 2 more slides. We took this concept and carried over to the field. This is where we need to be really measuring things. That's how we developed, with some funding from Army Corps of Engineers in the United States, a bender element field sensor, right? And here are the housings of the 2 piezoelectric source and the receiver sets, with a known distance in between them and the cables around, right? Buried in a constructed layer left of a granular material in this facility over a geogrid, right? This was actually a payment test section over in the Federal Aviation Administration Test Center, National Airport Payment Test Facility. And very first measurements from that in a compacted layer directly above, again, the geogrid. Geogrid is right here, directly above that PE1, about 1 inch, about 2.5 centimeters above. We could actually see an increase in shear wave velocity, whereas going up about 4 inches, about almost 10 centimeters above, the shear wave velocity is not that high. And in a actually unstabilized one, the south sections with no geogrid control section, similar values. So this is the way we think that we can actually use bender element technology, small strain measurements, shear waves, to quantify the mechanically stabilized stiffened zone. With that, I would like to come to the conclusion of my talk, but before I say thank you, I would like to mention about a major conference event coming up this May 24th through the 27th. That's the fourth International Conference on Transportation Geotechnics, ICTG 2021 now we call it. And it's going to be a virtual event sponsored by the Technical Committee 202 on Transportation Geotechnics. Now, I'd like to mention that IGS is 100% endorsed recently this event, because there's going to be a major, significant, I should say, coverage of geosynthetics papers and geosynthetics content in this conference. And IGS president himself will give a keynote lecture, Dr. Chun Se-gyu, professor from actually South Korea, geosynthetics in slopes and tunnels. We will have past president of IGS, Professor Jorge Zornberg, talking about geosynthetics and transportation. And we will also have Professor Buddhima Indiradna from Australia, talking about railroad and some sustainable applications with railroads. So plus other keynote speakers. One other aspect is that IGS North America also established a short course, a full-day short course that I'll be also teaching and involved with that with 2 of my colleagues from the US. So again, please consider visiting the website. Just type ICTG 2021 and you will get to the website, and registration is now open. So thank you for your attention. Hopefully I'm within my time limit here, and I'll be happy to answer any questions you might have.
Thank you, Erol. Very, very interesting presentation, and you were right on time. So that's very great. So I want to go straight to Corey's presentation. That will be a case study, I think, around 5 minutes, and then we start some questions. I have received some really interesting questions. We will get to some of them in the live event, but I will email the rest of them to Erol to answer later. Corey?
I'll stop sharing that. Okay, you cut them. All right, perfect.
Over to you, Corey.
Okay, excellent. Thank you, Simek. Thank you, Erol. That was an excellent presentation. I appreciate you sharing your expertise and providing some of that information. Very informative. And once again, thank you to the ACIGS and CMEC for all your organization and this lecture series or webinar series. It's been fantastic. I have a new favorite as of today, but I might be a bit biased. So I've got a couple minutes to lend some local context to the presentation today, and I'll have to race through and get motoring along to achieve that. So let's make a start. For any of you that aren't aware of geofabrics, just a quick introduction. We've been around for some time, since the late 70s. We've been operating in Australia. We manufacture materials at 2 different locations in Australia. We've got multiple testing facilities, one's NATA accredited laboratory, as well as a research and development laboratory here on the Gold Coast. Quite a large footprint as far as our distribution and sales offices to have the product where it's needed. And within our 200 employee workforce, there's a strong technical services division for any geosynthetic related design support that you may require in your endeavors. By all means, reach out to us and see if we can help you in some way. Myself, I've been with Geofabrics since 2008, and have been lucky enough to spend that time entirely in Queensland. One of my key customers has been Queensland Rail. We probably not the network that Erol alluded to in the United States, but prior to 2010, Queensland Rail operated a significant network, and I think the size of that network has led, at least lent itself partially to their uptake of the geosynthetic technology. And so we've been very lucky to have a rail administrator in Queensland Rail that have been open to considering geosynthetic. So certainly ballast stabilization is one of the primary applications, as we've heard about today, but other applications within the rail segment is drainage, erosion control, slope stabilization in the corridor, more generally speaking, and more recently, the mud pumping or contamination, migration of fines that Erol had alluded to. So we're going to look quickly at a local case study. This is in Brisbane. Yurong-Pili is the section of the Queensland Rail network just near Yurong-Pili Station. For anybody not from Brisbane, we're talking about just on the south side of the Brisbane CBD, near the Brisbane Tennis Center and near the Brisbane River there. They had a very poor performing section of track for many years. When we were approached by Queensland Rail, the conditions and certainly the concerns were the poor drainage, the mud pumping, and the constant maintenance. They had looked at maintenance, significant maintenance cycles at 2003, 2005, 2006, 11, and 13, and then approached us in 2015 to put forward some geosynthetic options for their consideration. So as we can see there through the cross section, we've got a bit of geotextile or separation geotextile, a couple layers of traction geogrids, and the TrackTex, which is an anti-mud pumping geocomposite, which is developed in the UK and has gained very widespread acceptance quite quickly due to its effectiveness. Does substitute for other filtration mediums like a sand layer, so on and so forth. The other condition that we had to try and cope with was the reduction of the capping layer by 150 mil, or by about a third of the depth. So that was that made it interesting, and hence the additional layer of geogrid. So Tensar Geogrids. Tensar developed the geogrid technology in the late 70s. We've been exclusive partners with Tensar since the mid-80s, and the triaxial geogrids have been in the market since about 2007. So one thing to think about when you're considering a geogrid for this application is really how is that going to interact with that material? Are we going to gain the lateral constraint or lateral confinement that Erol had alluded to? We didn't hear much talk about tensile strength within Erol's presentation. It's some of the other properties: the thickness of the rib, the integral junction of the geogrid, and the stiffness of that geosynthetic plane that leads to the performance in a tensor application. There is some other research which I was pleased to see Erol didn't have in his presentation at the University of Pennsylvania, where they've actually developed a wireless motion sensing ballast particle. And with that, have been able to establish within a rail formation under load what is actually transpiring with the movement of that ballast particle. They measured translational movement as well as vertical displacement, and certainly rotational movement, which is what we start to think about when two adjacent particles are grinding each other into more loose, rounded ballast. How can we reduce that actual mechanism? And this is just one slide. All this research, anything I'm referencing, we'd be more than happy to supply the full research papers. This is now seeing 2 phases of research, so some very interesting data coming from it. We can see there just on the rotational movement, the control section versus the formation with the reinforcing geogrid, and we basically eliminated that rotational movement with the inclusion of that geosynthetic. The other issue we were contending with at Pili was that mud pumping. You can see the migration of those fines up into the ballast layer, contaminating that layer. So the introduction or the use of the track text was taken on in 2015 for this, addresses mud pumping problems, much easier to install than some more traditional methods. Can be placed directly on the ballast. It protects and maintains the capping layers it's intended. And so there's other benefits. Again, we've got full research here, how this product came into development in the UK. It is registered as an improved material with Queensland Rail. So if you need to know more about mud pumping, you have a mud pumping application you're having to contend with, please let us have a chance to talk about that. So just a quick construction sequence there of the project, the removal of the existing poor performing formation. Then we've got the non-woven geotextile providing separation just beneath the triaxial 170 geogrid that's providing that benefit, that confinement to capping material, compaction of that capping material, and then placement of the anti-pumping geocomposite, the track text directly over the top of it. And then we've got another layer of the larger aperture ballast reinforcement product, the Trax TS19DL geogrids to provide that confinement to that ballast material. Last thing I'd mention, we did talk about sustainability and the ACigs focusing on sustainability. Geofabrics has done the same thing in the last 12 months with the development of our Bitumen Green. We realized a few years ago in Australia, we can't just keep exporting all of our waste to other countries. So we developed our Bitumen non-woven geotextile, which incorporates locally sourced recycled polymers. And through the development of Bitumen Green, we've got multiple products there that you can see that incorporate that Bitumen recycled geotextile onto it. For more sustainable outcomes, we need to find sustainable ways to develop these critical infrastructure projects. And we like to believe that Bitumen Green, through its widespread acceptance, is contributing to that. So without any further ado, I hope I made it in time for you, CMEC. We've got a great value proposition here at Geofabrics. If there's anything that we can land, please don't hesitate to reach out. And we'll do our best to help. Thank you, CMEC.
Thank you, Corey. So we don't have much time left. I received around 10 really interesting questions. The only reason I will only ask 2 of them is that 2 people asked these 2 same questions. So I just give priority to those 2 questions, but I'll definitely email the rest of the questions to Erol. And if you can kindly answer them in an email, we can distribute to the people who asked the questions. First one, multi-layer geogrids. What's the experience on that, and how do you think that will work in different applications?
In ballast, as I mentioned, we only have the experience in Illinois, well, in my research group with the triaxial specimens. However, not in a ballast layer, actual physical constructed ballast in the field. However, an unbound granular base layer, certainly I have experience with some test sections and placing 2 geogrids and how they work. So, yeah, that's where I will stay, I guess. Indeed.
Okay, perfect. And the second one, using geotextile and geogrid together as 2 separate material, or maybe as a composite material. What's the experience on that, and how that affects the performance of the ballast?
We have had many talks on this over the years. I mean, one aspect of having a geocomposite, with one side there is a textile or fabric, right? If fabric is not allowing the full penetration of an aggregate through the aperture, basically then that's probably not, in a way, not helping the geogrid to fully arrest and capture the movement of an aggregate particle, right? So that's the only negative that I usually hear from some of the, again, professionals in the field. But other than that, I think it will work in general. However, we want to make sure to take advantage of the full advantage of, I would say, the aperture strike option. And again, if the geotextile fabric already glued with the grid allows that, then no problem.
Okay. No worries. Perfect. Thanks, Erol and Corey, for interesting presentations. And like I said, I will email the rest of the questions to Erol, and we distribute the responses when we receive. So just a quick note before we finish, our next event is actually a live forum. That will be on the 24th of March, so just 2 weeks away from now. And we have like a panel of really famous people in the geosynthetics industry, from Professor Kerry Rowe. We have local experts, Fred Gassner, Warren Hornsey, and also we have Eric Blond from Canada and Boyd Ramsey. So very interesting panel to discuss barrier functions of geosynthetics. This will be our first forum for this year, but the plan is to have 4 of these throughout the year. So this first one is going to be on barriers, the second one on hydraulics, then we go to reinforcement and stabilization. So thanks again, everyone, for attending this webinar and listening to us. Thank you, Erol and Corey, for interesting presentations, and we will see you in our next event.
Thank you very much again.
Thank you. Bye.
Thanks.
Thanks, Simek. Thank you, Erol.
Thank you.